Did you know? Most Spark jobs don't fail during computation. They fail while reading data, not during map, not during processing, but during shuffle read. And the reason is simple. This is the most network-heavy, failure-prone part of Spark. Last time, we explored what happens on the map side of shuffle. We saw how Spark writes data to disk. But today, we follow the real battle, how reducers try to read that data. Shuffle read is hard because everything is distributed. Data is spread across machines, reducers depend on remote executors, and everything relies on the network. Now think about this. If even one machine fails, or one file is missing, the entire stage can fail. And that's why shuffle read is one of the most fragile parts of Spark. Now before we go deep, let's first understand the big picture. Once the map stage completes, Spark schedules the reduce stage. Each reduce task is responsible for one partition. But here's the catch. A reducer does not read from one place. It reads from every map task. Let's say 200 map tasks and 50 reduce tasks. Each reducer fetches from all 200 maps. That means 200 times 50 equals 10,000 fetch requests. And this is where things start getting intense. Now the obvious question is, how does a reducer even know where the data is? This is where Map Output Tracker comes in. It lives on the driver and acts like a directory service. During the map stage, it stores the information like which executor produced data, which partition it belongs to, how large the block is. So when a reducer starts, it simply asks, where is my data? Let's walk through this step by step. Reducer starts and contacts driver. Driver responds with something like, executor, a block, executor B block, executor C block. Now the reducer knows exactly where to go. And now comes the most important part. This is the engine behind shuffle read, and this is where most people get confused. Instead of sending random requests, Spark organizes everything. It groups blocks by executor, fetches them in parallel streams data as it arrives. You can think of it as a traffic controller, making sure thousands of requests don't collide. Now let's talk about how data actually moves. Spark uses Netty, a high-performance networking library. Each executor runs a server, so the flow becomes reducer to Netty, client to network, to executor, to Netty, server, to data. This is what enables Spark to handle massive parallel transfers. Let's visualize this clearly. Reducer sends a request, network carries it, executor responds with data, reducer receives and processes it. Simple flow, but happening thousands of times in parallel. Now let's step back. This is where things get crazy. We already saw 200 map times 50 reduce equals 10,000 requests. Imagine this at scale thousands, sometimes millions of network calls. And if the network slows down, the entire job slows down. And this is exactly where most failures happen. We get an error fetch failed exception. This happens when executor crashes, file is missing, network fails, disk issues. If even one block is missing, the reducer cannot continue. But Spark doesn't give up immediately. It retries. Configs like spark.shuffle.io.max retries, spark.shuffle.io.retry. Wait, if retry works, job continues. If not, Spark has to recompute the entire stage. And that can be very expensive. So how do we detect these issues? Using Spark UI. Key metrics. Remote blocks fetched. Remote bytes read. Fetch wait time. Fetch wait time is the most important. If it's high, your job is waiting on the network. Here's the entire flow in simple words. First, the reducer contacts the driver. The driver uses the map output tracker to find where data exists. Then the reducer connects to executors. Data is transferred over the network using NetI. Blocks are fetched, merged, and finally computed. Simple on the surface, but internally, a lot is happening. Now imagine this situation. A map executor creates shuffle files, but crashes before reducers fetch them. What happens? Files are gone, reducers fail, stage recomputes. And this is why Spark introduced External Shuffle Service. It keeps shuffle data alive, even if executors die. Now before we wrap up, let's quickly switch hats. Imagine you're sitting in a Spark interview. Here are some questions that interviewers frequently ask from today's topic. Question 1. What is the role of Map Output Tracker? The answer is, it stores metadata about shuffle outputs and helps reducers locate shuffle blocks created by map tasks. Question 2. Why is shuffle read considered expensive? The answer is, because it involves network communication, disk I/O, memory usage, and coordination across multiple executors. Question 3. What does Shuffle Block Fetcher Iterator do? The answer is, it manages fetching shuffle blocks from executors, groups requests, performs parallel fetching, and handles retries. Question 4. What is Fetch Failed Exception? The answer is, it occurs when a reducer cannot retrieve a required shuffle block due to executor loss, missing files, network issues, or disk failures. Question 5. How does Spark recover from shuffle fetch failures? The answer is, Spark retries fetching the block. If retries fail, Spark may rerun previous stages to regenerate the missing shuffle data. Question 6. What metrics would you check for shuffle-related performance issues? The answer is, I would check remote blocks fetched, remote bytes read, shuffle read size, and especially fetch wait time in Spark UI. If you can confidently answer these 6 questions, you're already ahead of many Spark candidates. Let's summarize everything we learned today. 1. Reducers must fetch data from all map tasks. 2. Map Output Tracker helps reducers locate shuffle blocks. 3. Shuffle Block. Fetcher Iterator manages block fetching. 4. NetI powers Spark's high-performance network transfers. 5. Large shuffles create significant network traffic. 6. Fetch failures are one of the most common production issues. 7. Spark retries failed fetches before recomputing stages. 8. Spark UI provides critical metrics for troubleshooting shuffle problems. 9. External Shuffle Service helps preserve shuffle data even when executors disappear. And perhaps the biggest lesson, in distributed systems, moving data is often harder than processing data. So next time your Spark job slows down, don't immediately blame your transformations, don't immediately blame memory, and don't immediately blame the cluster. Follow the data. Look at the shuffle. Look at the network. Look at the fetch wait times. Because many Spark performance problems are actually data movement problems. And once you understand the shuffle read path, you've crossed one of the biggest milestones in understanding Spark internals. But we're still missing one important piece of the puzzle. What happens when an executor creates shuffle files and then suddenly dies? Do reducers lose access to the data? Does Spark recompute everything? Or is there a mechanism that protects those shuffle files? In the next video, we'll take a deep dive into External Shuffle Service. We'll see how Spark preserves shuffle data, supports dynamic allocation, and avoids expensive recomputations in production clusters. Trust me, if you've ever worked with Spark in production, you'll want to understand this component. See you in the next video.